What I'm going to try and do in the next 15 minutes or so is tell you about an idea of how we're going to make matter come alive. Now, this may seem a bit ambitious, but when you look at yourself, you look at your hands, you realize that you're alive. So this is a start. Now, this quest started 4 billion years ago on planet Earth. There's been 4 billion years of organic biological life. And as an inorganic chemist, my friends and colleagues make the distinction between the organic living world and the inorganic dead world. And what I'm going to try and do is plant some ideas about how we can transform inorganic dead matter into living matter, into inorganic biology. Before we do that, I want to kind of put biology in its place. And I am absolutely enthralled by biology. I love to do synthetic biology. I love things that are alive. I love manipulating the infrastructure of biology. But within that infrastructure, we have to remember that the driving force for biology is really coming from evolution. And evolution, although it was established well over 100 years ago by Charles Darwin and a vast number of other people, evolution still is a little bit intangible. And when I talk about Darwinian evolution, I mean one thing only, that is survival of the fittest. And so forget about evolution in a kind of metaphysical way. Think about evolution in terms of offspring competing and some winning. So bearing that in mind, as a chemist, I wanted to ask myself the question, frustrated by biology, is what is the minimal unit of matter that can undergo Darwinian evolution? And this seems quite a profound question. And as a chemist, we're not used to profound questions every day. So when I thought about it, then suddenly I realized that biology gave us the answer. And in fact, the smallest unit of matter that can evolve independently is in fact a single cell, a bacteria. So this raises three really important questions. What is life? Is biology special? Biologists seem to think so. Is matter evolvable? Now, if we answer those questions in reverse order, the third question, is matter evolvable? If we can answer that, then we're going to know how special biology is, and maybe, just maybe, we'll have some idea of what life really is. So here's some inorganic life. This is a dead crystal, and I'm going to do something to it, and it's going to become alive. And you can see it's kind of pollinating, germinating, growing. This is an inorganic tube, and all these crystals here under the microscope were dead a few minutes ago, and they look alive. Of course, they're not alive. It's a chemistry experiment where we've made a crystal garden. But when I saw this, I was really fascinated because it seemed lifelike. And as I pause for a few seconds, have a look at the screen. You can see this architecture growing, filling the void. And this is dead. So I was kind of positive that if somehow we can make things mimic life, let's go one step further. Let's see if we can actually make life. But there's a problem, because up until maybe a decade ago, we were told that life was impossible and that we were the most incredible miracle in the universe. In fact, we were the only people in the universe. Now, that's a bit boring. So as a chemist, I wanted to say, well, okay, hang on. What is going on here? Is life that improbable? And this is really the question. I think that perhaps the emergence of the first cells was as probable as the emergence of the stars. And in fact, let's take that one step further. Let's say that if the physics of fusion is encoded into the universe, maybe the physics of life is as well. And so the problem with chemists, and this is a massive advantage as well, is we like to focus on our elements. In biology, carbon takes center stage. And in a universe where carbon exists, and organic biology, then we have all this wonderful diversity of life. In fact, we have such amazing life forms that we can manipulate. We're awfully careful in the lab to try and avoid various biohazards. But what about matter? If we can make matter alive, would we have a matter hazard? So think, it's a serious question. If your pen could replicate, that would be a bit of a problem. So we have to think differently if we're going to make stuff come alive, and we also have to be aware of the issues. But before we can make life, let's think for a second what life really is characterized by. And forgive the complicated diagram, this is just a collection of pathways in the cell. And the cell is obviously, for us, a fascinating thing. Synthetic biologists are manipulating it. Chemists are trying to study the molecules to look at disease. And you have all these pathways going on at the same time. You have regulation, information is transcribed, catalysts are made, stuff is happening. But what does a cell do? Well, it divides, it competes, it survives. And I think that is where we have to start in terms of thinking about building from our ideas in life. But what else is life characterized by? Well, I like to think of it as a flame in a bottle. And so what we have here is a description of single cells replicating, metabolizing, burning through chemistry. And so we have to understand that if we're going to make artificial life or understand the origin of life, we need to power it somehow. So before we can really start to make life, we have to really think about where it came from. And Darwin himself mused in a letter to a colleague that he thought that life probably emerged in some warm little pond somewhere. Maybe not in Scotland, maybe in Africa, maybe somewhere else. But the real honest answer is we just don't know, because there is a problem with the origin. If you imagine way back 4.5 billion years ago, there was a vast chemical soup of stuff. And from this stuff, we came. So when you think about the improbable nature of what I'm going to tell you in the next few minutes, just remember, we came from stuff on planet Earth. And we went through a variety of worlds. The RNA people would talk about the RNA world. We somehow got to proteins and DNA. We then got to the last ancestor. Evolution kicked in, and that's the cool bit. And here we are. But there's a roadblock that you can't get past. You can decode the genome, you can look back, you can link us all together by mitochondrial DNA, but we can't get further than the last ancestor, the last visible cell that we could sequence or think back in history. So we don't know how we got here. So there are two options. Intelligent design, direct and indirect, so God or my friend. Now, talking about ET putting us there or some other life just pushes the problem further on. I'm not a politician, I'm a scientist. So the other thing we need to think about is the emergence of chemical complexity. This seems most likely. So we have some kind of primordial soup, and this one happens to be a good source of all 20 amino acids. And somehow, these amino acids are combined and life begins. But life begins. What does that mean? What is life? What is this stuff of life? So in the 1950s, Miller-Urey did their fantastic chemical Frankenstein experiment, and where they did the equivalent in the chemical world. They took the basic ingredients, put them in a single jar, and ignited them, and put a lot of voltage through, and they had a look at what was in the soup, and they found amino acids. But nothing came out, there was no cell. So the whole area has been stuck for a while, and it got reignited in the 80s when analytical technologies and computer technologies were coming on. In my own laboratory, the way we're trying to create inorganic life is by using many different reaction formats. So what we're trying to do is do reactions not in one flask, but in tens of flasks and connect them together, as you can see with this flow system, all these pipes. We can do it microfluidically, we can do it lithographically, we can do it in a 3D printer, we can do it in droplets with colleagues. And the key thing is to have lots of complex chemistry just bubbling away. But that's probably going to end in failure. So we need to be a bit more focused. And the answer, of course, lies with mice. And this is how I remember what I need as a chemist. I'm always thinking, well, I want molecules, okay? But I need a metabolism. I need some energy. I need some information. And I need a container, because if I want evolution, I need containers to compete. So if you have a container, you know, it's like getting in your car. This is my car, and I'm going to drive around and show you off my car. And I imagine you have this similar thing in cellular biology at the emergence of life. So these things together give us evolution, perhaps. And the way to test it in the laboratory is to make it minimal. So what we're going to try and do is come up with an inorganic Lego kit of molecules. And so forgive the molecules on the screen, but these are a very simple kit. There's only maybe 3 or 4 different types of building block present, and we can aggregate them together and make literally thousands and thousands of really big nanomolecular molecules, the same size of DNA and proteins, but there's no carbon in sight. Carbon is banned. And so with this Lego kit, we have the diversity required for complex information storage without DNA. But we need to make some containers. And just a few months ago in my lab, we were able to take these very same molecules and make cells with them. And you can see on the screen a cell being made, and we're now going to put some chemistry inside and do some chemistry in this cell. And all I wanted to show you is we can set up molecules in membranes, in real cells, and then it sets up a kind of molecular Darwinism, a molecular survival of the fittest. And this movie here shows this competition between molecules. Molecules are competing for stuff. They're all made of the same stuff, but they want their shape to win. They want their shape to persist. And that is the key. If we can somehow encourage these molecules to talk to each other and make the right shapes and compete, they will start to form cells that will replicate and compete. If we manage to do that, forget the molecular detail, and let's zoom out what that could mean. So we have this special theory of evolution that applies only to organic biology, to us. If we could get evolution into the material world, then I propose we should have a general theory of evolution. And that's really worth thinking about. Does evolution control the sophistication of matter in the universe? Is there some driving force through evolution that allows matter to compete? And so that means we could then start to develop different platforms for exploring this evolution. So you imagine if we're able to create a self-sustaining artificial life form, that not only will this tell us about the origin of life, that it's possible, that the universe doesn't need carbon to be alive, it can use anything, we can then take one step further and develop new technologies, because we could then use software control for evolution to code in. So imagine we make a little cell, we want to put it out in the environment, and we want it to be powered by the sun. All we do is we involve it in a box with a light on. And we don't use design anymore. We find what works. We should take our inspiration from biology. Biology doesn't care about the design unless it works. So this will reorganize the way we design things. But not only just that, we will start to think about how we can start to develop a symbiotic relationship with biology. Wouldn't it be great if you could take these artificial biological cells and fuse them with biological ones to correct problems that we couldn't really deal with? The real issue in cellular biology is we are never going to understand everything because it's a multidimensional problem put there by evolution. Evolution cannot be cut apart. You need to somehow find the fitness function. And the profound realization for me is that if this works, the concept of the selfish gene gets kicked up a level, and we really start talking about selfish matter. And what does that mean in a universe where we are right now the highest form of stuff? You are sitting on chairs. Okay, they're inanimate, they're not alive, but you are made of stuff, and you are using stuff, and you enslave stuff. So using evolution in biology and in inorganic biology, for me, is quite appealing, quite exciting. And we are really becoming very close to understanding the key steps that makes dead stuff come alive. And again, when you're thinking about how improbable this is, remember, 5 billion years ago, we were not here, and there was no life. So what will that tell us about the origin of life and the meaning of life? But perhaps, for me as a chemist, I want to keep away from general terms. I want to think about specifics. So what does it mean about defining life? We really struggle to do this. And I think if we can make inorganic biology and we can make matter become evolvable, that will in fact define life. I propose to you that matter that can evolve is alive. And this gives us the idea of making evolvable matter. Thank you very much. So you need to come down?
Just a quick question on timeline. I mean, you believe you're going to be successful in this project? When?
So many people think that life took millions of years to kick in. We're proposing to do it in just a few hours, once we've set up the right chemistry. So,
and when do you think that will happen?
Hopefully within the next 2 years.
That would be a big story. In your own mind, what do you believe the chances are that walking around on some other planet is non-carbon-based life, walking or oozing or something?
I think it's 100%. Because the thing is, we are so chauvinistic to biology. if you take away carbon, there's other things that can happen. So the other thing, that if we're able to create life that's not based on carbon, maybe we can tell NASA what really to look for. Don't go and look for carbon, go and look for evolvable stuff.
Lee Cronin, good luck.
Thank you very much.